This meeting is being recorded.
For chapter 15, problem number 5 here, we're asked to identify the number of signals that we expect to see with a proton NMR spectrum for these following compounds. So I will walk through each of these compounds and point out the reasons why we expect to see these signals. So in our first compound here, we're going to see a total of 8 different signals. So that's going to be for compound A here. So first, we see these 3 methyl protons. These are always going to be chemically equivalent. So that's our first signal here. Then we have this proton here. This is going to have a distinct environment here. So that's the second signal that we'll see. Here we have again, these would be 2 chemically equivalent protons here, so this would be our third signal. And then on the end here, we see 3 protons of a methyl group, again, always chemically equivalent, so our fourth signal there produced. Now let's move to the left. We're going to have a proton here. This will be our fifth signal. Then we have another lone proton here, the sixth signal. Then we have 2 more seen here. That would be chemically equivalent. So this would be our seventh signal. And then last we have, once again, 3 protons of a methyl group here, which are all chemically equivalent. So that's our eighth signal seen right here. So again, compound A would have 8 total signals. Now, let's look at compound B. Compound B, we would expect to see 4 distinct signals. So let's start over here. So these 3 protons of this methyl group would produce our first signal. Then we have these 2 protons here. These will be equivalent in the same environment near that methyl group, for example, or that methoxide group. So both of these would produce a second signal. Then we have these 2 protons here. These would both produce the third signal that's expected. And last we have these 3 protons here would produce the fourth signal. And again, the 3 protons of a methyl group are always going to be chemically equivalent. And then through this axis of symmetry seen in the middle of the molecule here, both protons for group 2 and 3 are chemically equivalent. Let's take a look at compound C here. This will have only 2 distinct types of signals. So we would see 3 protons here. These 2 methyl groups can be interchanged through rotational symmetry. So these 6 protons here would be chemically equivalent. So that's our first signal. And then we would see these 4 protons here would be chemically equivalent due to interchange by rotational symmetry. So they would produce that second signal. Then let's take a look at compound D here. We should see 3 different kinds of protons. So these 6 protons here, each 3 of these methyl groups would produce the first signal. Then we have these 2 protons here. So these 2 would produce a second signal. And then we have these last 2 protons here. These would produce a third signal. Again, due to an axis of symmetry here and interchange, that's why the 2 protons in group 2 and 3 would each produce a single signal. They are chemically equivalent. So let's take a look at compound E here. We'll move a little quicker here. So we're going to produce 5 signals now for compound E. So let's chart these 5. So here, these 3 in this methyl group would produce the first signal. This proton here would produce our second signal. Then we move over here. This is our third signal. Moving along, we have our fourth signal with that proton there. And then closest to our chlorine here, we would see that fifth signal produced. All right, now let's take a look at compound F. Due to some symmetry, this compound will only have three distinct signals. So we have up here our first, then we have down here, and this proton here would produce the second signal, and then this third signal would be produced by this chemically distinct proton at the bottom here. The two would be chemically equivalent due to an axis of symmetry, rotational symmetry. So that's why the two protons in group 2 are chemically equivalent. Let's look at structure G here. So now we have 4 protons, and none of these 4 protons can be interchanged by rotational or reflectional symmetry. So each of these 4 protons would occupy a unique electronic environment. So we would have 4 signals here, right? So we have 1, 2, 3, 4 chemically distinct environments for these protons, 4 signals. All right, and then lastly, we'll take a look at structure H here. This compound, again, due to reflectional and rotational symmetry, we would see these 4 groups of methyl protons would be chemically equivalent. Again, they can be interchanged due to rotational symmetry. And then we see these 2 protons here can be interchanged again due to rotational symmetry. So those are chemically equivalent. So in this last compound that we'll look at here, we see 2 distinct signals.